Hey guys, tonight we're exploring the origin of the universe by presenting a summary of Stephen Hawking's book, A Brief History of Time. But don't worry, you don't need to be a physicist to understand this summary. Before you get comfortable, take a moment to like this video and subscribe, but only if you genuinely enjoy what I'm doing here. And let me know in the comments where you are tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now, dim lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Introduction. Meeting a cosmic detective. Imagine you're a detective, but instead of solving crimes, you're solving the mysteries of existence itself. That's exactly what Stephen Hawking did when he wrote A Brief History of Time in 1988. Think of this book as the ultimate mystery novel, where the crime scene is the entire universe, and the clues are scattered across billions of years and trillions of miles. Hawking had an extraordinary challenge. He wanted to explain the deepest secrets of reality without using a single mathematical equation. It's like trying to explain music without playing a single note, or describing color to someone who's never seen. Yet somehow, this brilliant physicist managed to do it, and his book became one of the most successful science books ever written, selling over 25 million copies worldwide. But here's what makes Hawking truly special. He didn't just want to tell us facts about the universe. He wanted us to feel the wonder of it all. He wanted us to understand that we're not just observers of this cosmic story, we're participants in it. Every atom in your body was forged in the heart of a dying star. You are literally made of stardust. And that's not poetry, that's physics. Chapter 1. Our picture of the universe. The Great Awakening. Let me start with Hawking's favorite story. There was once an elderly woman who attended a science lecture about how Earth orbits the sun. Afterward, she approached the speaker and said, "That's all nonsense. The world is really a flat plate supported on the back of a giant tortoise." When the scientist asked what the tortoise stands on, she replied triumphantly, "You're very clever, young man, but it's turtles all the way down." This story isn't meant to mock anyone. It's meant to show us something profound about human nature. We've always tried to make sense of our universe, and sometimes our first guesses are wonderfully creative, even if they're wrong. The history of science is really the story of humans gradually replacing turtles all the way down with something even more amazing: the actual truth. Picture ancient Greece, where brilliant thinkers like Aristotle looked up at the night sky and tried to make sense of what they saw. Aristotle was like a cosmic architect, designing a universe with Earth at the center, and everything else, the moon, sun, planets, and stars, arranged in perfect crystalline spheres around us. It was beautiful, elegant, and completely wrong. But it was wrong in an important way. It was the best explanation available at the time, based on careful observation. Think of scientific progress like climbing a mountain. Each generation of scientists climbs a little higher, sees a little further, and can spot the mistakes of those who came before. But here's the crucial part. They can only climb higher because they're standing on the shoulders of the previous climbers. When Copernicus came along in 1514, he made a revolutionary suggestion. What if Earth isn't the center of everything? What if we're just one planet among many, all orbiting the sun? This was like suggesting that your house isn't the center of your neighborhood. The whole neighborhood revolves around the local coffee shop instead. It turned our cosmic perspective completely upside down. But Copernicus was just the beginning. Galileo pointed the newly invented telescope at the sky and became the first human being to see the moons of Jupiter. Imagine his wonder and terror when he realized that here were objects that clearly weren't orbiting Earth. It was like discovering that not everyone in the world speaks your language. Suddenly, Earth didn't seem quite so central to everything. Johannes Kepler took this revolution even further. The ancients believed that celestial motion had to be perfectly circular because circles were perfect shapes. But Kepler discovered that planets actually move in ellipses, slightly squashed circles. It was as if the universe was saying, "Sorry, but I don't care about your ideas of perfection. I have my own rules." Then came Isaac Newton, perhaps the most brilliant detective in our cosmic mystery story. Newton didn't just describe what the planets do, he explained why they do it. His law of universal gravitation showed that the same force that makes an apple fall from a tree also keeps the moon in its orbit. It's the same force that holds you to the ground and keeps Earth circling the sun. Suddenly, the entire universe was revealed to be connected by invisible threads of gravity. But Newton's universe came with a troubling implication. If you could know the exact position and velocity of every particle in the universe at one moment, you could, in principle, calculate the entire future and past of everything. The universe would be like a gigantic clockwork mechanism, predictable and predetermined. This idea, called determinism, suggested that free will might be an illusion. Hawking also introduces us to one of the oldest questions in human thought. Did the universe have a beginning? Aristotle thought it had always existed, eternal and unchanging. Religious thinkers like St. Augustine believed in a moment of creation. Immanuel Kant argued that asking, "When did time begin?" was like asking, "What color is the number 7?" A meaningless question.
But the 20th century brought a stunning discovery that would change everything. The universe is expanding. If you run the cosmic movie backward, everything converges to a single point between 10 and 20 billion years ago. This was the birth of the Big Bang theory, and as Hawking noted with his characteristic wit, an expanding universe does not preclude a creator, but it does place limits on when he might have carried out his job.
Chapter 2. Space and Time. The Fabric of Reality. Now we come to one of the most mind-bending chapters in our cosmic detective story. Everything you think you know about space and time, throw it out the window. Or rather, prepare to see it in a completely new way. Let's start with a simple question. If you're sitting in a smoothly moving train with the windows closed, can you tell that you're moving? Galileo realized the answer is no. Motion, he discovered, is relative. You can only say you're moving compared to something else. This might seem obvious, but it has profound implications. Newton built on this idea, but added something that seemed like common sense. Time. Surely, Newton thought, time flows the same for everyone, everywhere. If I measure a minute with my stopwatch and you measure a minute with yours on the other side of the galaxy, we'll get exactly the same result. Time, in Newton's universe, was like a cosmic metronome, keeping the same beat throughout the entire universe. This seemed so obviously true that no one questioned it for over 200 years. It's like assuming that up means the same thing everywhere in the universe. It feels like it should be true. But then came a puzzle that changed everything. Scientists discovered that light travels at a specific speed, about 186,000 miles per second. That's fast enough to circle Earth's equator more than 7 times in a single second. But here's the weird part. No matter how fast you're moving when you measure the speed of light, you always get the same answer.
Think about this carefully, because it's
Genuinely strange. If you're in a car traveling 60 miles per hour and another car passes you at 70 miles per hour, that car appears to be moving at 10 miles per hour relative to you. This is basic common sense. But light doesn't behave this way. Whether you're standing still or racing toward a beam of light at incredible speed, that light always appears to be moving at exactly the same speed relative to you. This is where Einstein enters our story like a cosmic magician, ready to reveal that reality is far stranger and more wonderful than anyone imagined. Einstein realized that if the speed of light is constant for all observers, then something else has to give. And that something is our concepts of space and time themselves. Einstein's special theory of relativity, published in 1905, revealed that space and time are not separate, absolute things. They're woven together into a single fabric called space-time. And this fabric can stretch, compress, and warp. Time isn't a universal constant. It's more like a rubber band that can be stretched or compressed depending on how fast you're moving. Here's the mind-bending part. If you travel very fast, say 90% the speed of light, time actually slows down for you compared to someone who's standing still. It's not that your watch breaks. Time itself runs slower. If you took a journey to a nearby star at nearly light speed and came back, you might find that while you've aged 1 year, everyone on Earth has aged 10 years. It's like stepping into a time machine. Einstein also revealed something even stranger. Mass and energy are different forms of the same thing. His famous equation E=mc² tells us that a tiny amount of mass can be converted into an enormous amount of energy. The c² in that equation represents the speed of light multiplied by itself, a truly huge number. This is why nuclear reactions release so much energy, and why the sun can burn for billions of years by converting just a tiny fraction of its mass into light and heat. But Einstein wasn't finished reshaping our understanding of reality. 10 years later, he published his general theory of relativity, which revealed that gravity isn't really a force at all. Instead, mass and energy actually bend the fabric of space-time itself. Imagine placing a bowling ball on a stretched rubber sheet. It creates a depression. Now, roll a marble nearby and it will curve toward the bowling ball, not because the ball is pulling it, but because the rubber sheet itself is curved. This is how gravity really works. Earth doesn't pull you downward. Instead, Earth's mass warps space-time, and you're simply following the straightest possible path through this curved space. Light, too, follows these curves, which is why we see stars in slightly different positions when the sun's gravity bends their light during a solar eclipse. General relativity made a startling prediction. The universe itself must be either expanding or contracting. Space itself has a dynamic quality. It's not just an empty stage where matter performs. It's a participant in the cosmic drama. This prediction seemed so strange that even Einstein initially rejected it, adding a cosmological constant to his equations to keep the universe static. He later called this his biggest blunder.
Chapter 3. The Expanding Universe. Cosmic Growth.
Imagine you're an ant living on the surface of a balloon, and someone is slowly inflating it. From your perspective, every other ant on the balloon appears to be moving away from you. The farther away an ant is, the faster it seems to be receding. You might conclude that you're at the center of some great ant exodus. But actually, every ant sees the same thing, from its own perspective. No one is at the center, because it's the balloon itself that's expanding. This is exactly what's happening to our universe, and the discovery of this cosmic expansion is one of the most profound revelations in human history. The story begins with the challenge of measuring the vast distances to stars and galaxies. Imagine trying to figure out how far away a streetlight is at night when you can only see the light, not the post. Early astronomers faced this exact problem on a cosmic scale. The breakthrough came when Edwin Hubble discovered a type of star that acts like a cosmic lighthouse with a built-in distance meter. These stars, called Cepheid variables, pulsate like a cosmic heartbeat. Here's the beautiful part. The rate at which they pulse is directly related to how bright they truly are. It's as if each star carries an ID tag that says, "I pulse every 3 days, which means my true brightness is X." By comparing how bright these stars appear from Earth with how bright they actually are, Hubble could calculate their distance, using the same principle that tells you a car's headlights are far away when they look dim. This technique revealed something shocking. Our Milky Way galaxy, with its 100 billion stars, is just one galaxy among countless billions of others scattered throughout space. But Hubble's most revolutionary discovery came in 1929. When he examined the light from distant galaxies, he found something extraordinary. The light was redshifted. This is the cosmic equivalent of the Doppler effect that makes an ambulance siren sound lower in pitch as it drives away from you. When a galaxy is moving away from us, its light gets stretched to longer, redder wavelengths.
Here's what made Hubble's observation truly earth-shattering. He discovered that the more distant a galaxy is, the faster it's moving away from us. This wasn't random motion. It was a systematic pattern that could only mean one thing. The universe itself is expanding. Think about this carefully. It's not that galaxies are flying away from us through empty space. Space itself is growing, carrying the galaxies along with it like raisins in a rising loaf of bread. As the bread rises, every raisin moves away from every other raisin, even though none of them are actually moving through the bread. This discovery had mind-boggling implications. If the universe is expanding now, it must have been smaller in the past. Run the cosmic movie backward, and everything converges to an unimaginably hot, dense point roughly 13.8 billion years ago. This was the birth of the Big Bang Theory, the idea that our entire universe began from something smaller than a pinpoint and has been expanding and cooling ever since. Einstein, who had tried to keep the universe static in his equations, was initially resistant to this idea. But when he saw Hubble's evidence, he admitted his error. The cosmological constant he had added to prevent expansion, which he called his biggest blunder, actually turned out to be prophetic. Modern observations suggest that space itself has a built-in tendency to expand, driven by mysterious, dark energy. The expanding universe model received stunning confirmation in 1964 when two scientists accidentally discovered the cosmic microwave background radiation, the afterglow of the Big Bang itself. It's like finding the warm ashes of a fire that burned billions of years ago. This faint radiation fills all of space and carries the imprint of the universe when it was only 380,000 years old and first became transparent to light. Imagine the early universe as an incredibly hot, dense fog, so thick that light couldn't travel through it. As the universe expanded and cooled, this fog cleared in a moment cosmologists call recombination. The light that was suddenly free to travel has been journeying through space ever since, cooling and redshifting until it now appears as microwave radiation. When you tune a radio between stations and hear static, about 1% of that static is actually the echo of the Big Bang. The expansion of the universe also solved an ancient paradox. If the universe were infinite, static, and filled with stars, why is the night sky dark? Every direction you look should eventually hit a star, making the night sky blazing white. But in an expanding universe that had a beginning, light from the most distant objects hasn't had enough time to reach us yet, and the expansion redshifts much of the light beyond what our eyes can see.
Chapter 4: The Uncertainty Principle, the Quantum Revolution.
Now we enter perhaps the strangest chapter of our cosmic detective story, a realm where common sense breaks down completely and reality becomes fundamentally uncertain. Welcome to the quantum world, where particles can be in multiple places at once, where observation changes reality, and where the very act of knowing prevents us from knowing everything. For centuries, scientists believed in what's called determinism. Picture the universe as a giant clockwork machine, with every gear, spring, and pendulum following precise laws. The great mathematician Laplace argued that if you could know the exact position and speed of every particle in the universe at any given moment, you could predict the entire future and past with perfect accuracy. It's like saying that if you could freeze a movie at any frame and examine it perfectly, you could figure out what happens in every other frame. This mechanical view of the universe was deeply satisfying. It suggested that chance was just ignorance. If something seemed random, it was only because we didn't have enough information. But the early 20th century was about to shatter this comfortable certainty forever. The first crack appeared with something called the ultraviolet catastrophe. When scientists tried to predict how much energy a hot object should radiate, their calculations suggested it should emit infinite energy. Clearly impossible. It was like having a theory that predicted every light bulb should burn with the brightness of 1,000 suns. Max Planck solved this puzzle in 1900 with a radical idea. Energy isn't continuous like water flowing from a tap. Instead, it comes in discrete chunks or packets called quanta. It's as if energy can only be delivered in specific coin denominations. You can have 1 quantum or 2 quanta, but never 1.5 quanta.
This quantum idea was revolutionary, but its full implications weren't understood until Werner Heisenberg made an even more startling discovery. Heisenberg realized that there's a fundamental limit to what we can know about reality. His uncertainty principle states that you cannot simultaneously know both the exact position and exact momentum of a particle. The more precisely you measure one, the more uncertain the other becomes. This isn't just a limitation of our measuring instruments, it's a fundamental feature of reality itself. Think of it this way. To see something, you need to shine light on it. But light carries energy, and when that energy hits a tiny particle, it disturbs the particle's motion. It's like trying to measure the position of a ping pong ball in a dark room by throwing bowling balls at it. You'll find the ball, but you'll completely change its motion in the process. But the quantum world gets even stranger. Particles exhibit what's called wave-particle duality. Sometimes light behaves like a wave, creating interference patterns just like ripples on a pond. Other times it behaves like a stream of particles called photons. It's as if reality can't decide what it wants to be, and chooses based on how we observe it. The famous double-slit experiment demonstrates this beautifully. Shoot individual particles of light at a barrier with 2 slits, and they create an interference pattern on the other side, just like waves. But here's the mind-bending part. Each particle somehow seems to go through both slits simultaneously and interfere with itself. Place a detector at one of the slits to see which path each particle takes, and the interference pattern disappears. The very act of observation changes the behavior of reality. Chapter 5. Elementary Particles and Forces. The Universe's Building Blocks. Imagine you're a cosmic architect, and you want to build a universe. What would you need in your toolbox? You'd need building materials, the fundamental particles that make up everything. And you'd need forces, the invisible hands that shape how these particles interact. Welcome to the subatomic world, where the universe reveals its deepest construction secrets. Our understanding of matter has come a long way from the ancient Greeks, who thought everything was made of tiny, indivisible particles called atoms, from the Greek word meaning uncuttable. For over 2,000 years, this remained just a philosophical idea. But in the early 20th century, scientists began to discover that atoms aren't indivisible at all. They're more like tiny solar systems, with a dense nucleus surrounded by orbiting electrons. But the story doesn't end there. The nucleus itself turned out to be made of protons and neutrons, and in the 1960s, scientists discovered that even protons and neutrons aren't fundamental. They're made of smaller particles called quarks. It's like opening a Russian doll, only to find another doll inside, and another inside that. Quarks come in 6 different types, which physicists whimsically named flavors: up, down, strange, charm, bottom, and top. Don't let these names fool you. They have nothing to do with actual taste. They're just labels, like calling baseball positions first base and shortstop. Each quark also carries one of 3 colors: red, green, or blue, which again has nothing to do with actual color. It's just another property,
like electric charge.
Here's where the story gets fascinating. You can never find a quark by itself. They're always bound together in groups, held by the strongest force in the universe, the strong nuclear force. This force has a peculiar property called color confinement. Try to pull two quarks apart, and the force between them actually gets stronger, like stretching a rubber band. Pull hard enough and you'll create new quarks rather than separate the original ones. It's as if the universe has a strict no singles policy for quarks. Protons and neutrons are made of 3 quarks each. A proton contains 2 up quarks and 1 down quark, while a neutron has 2 down quarks and 1 up quark. The difference between these combinations is what makes protons positively charged and neutrons electrically neutral. It's amazing to think that the entire chemical complexity of our world, every element in the periodic table, comes from different arrangements of just these 2 types of quarks and electrons. But particles are only half the story. To understand how the universe works, we also need to understand the forces that govern particle interactions. There are 4 fundamental forces, and each one is carried by special particles called bosons. Think of these force-carrying particles as the universe's messengers, constantly being exchanged between particles to create the forces we observe. The electromagnetic force is carried by photons, particles of light. This force is responsible for electricity, magnetism, and light itself. Every time you flip a light switch, see a rainbow, or use your cell phone, you're witnessing the electromagnetic force in action. It's also what holds atoms together by attracting negatively charged electrons to positively charged protons. The weak nuclear force is carried by particles called W and Z bosons. This force is responsible for certain types of radioactive decay and plays a crucial role in the nuclear fusion reactions that power the sun. Without the weak force, the sun couldn't shine and life on Earth wouldn't exist. The strong nuclear force, carried by gluons, is what holds atomic nuclei together. Despite its name, it's actually the strongest of all forces, but it only operates over incredibly short distances, about the size of an atomic nucleus. If the strong force were just slightly weaker, protons and neutrons couldn't stick together, and there would be no atoms heavier than hydrogen in the universe. Finally, there's gravity, the force we're most familiar with but understand the least. Gravity is thought to be carried by hypothetical particles called gravitons, though these have never been directly observed. Gravity is by far the weakest force. A small magnet can easily overcome the gravitational pull of the entire Earth when it picks up a paperclip. But gravity has unlimited range and is always attractive, so it dominates on large scales, shaping the structure of planets, stars, and galaxies. Here's something remarkable. At extremely high temperatures, these forces begin to merge together. The electromagnetic and weak forces unite into a single electro-weak force at energies that existed just after the Big Bang. Scientists believe that at even higher energies, the strong force joins with the electro-weak force in what's called a grand unified theory. And at the ultimate energy scale, the Planck energy, all 4 forces, including gravity, may unify into a single superforce. This quest for unification isn't just academic. It goes to the heart of what we mean by understanding the universe. If we could find a single theory that explains all forces and particles, we would have something approaching a complete description of physical reality. It would be like having the universe's instruction manual, written in the language of mathematics. The standard model of particle physics, developed over decades, successfully describes 3 of the 4 forces and predicts the existence of particles that were later discovered experimentally. The recent discovery of the Higgs boson, which gives other particles their mass, was a triumph for this theoretical framework. But the standard model is incomplete. It doesn't include gravity. It can't explain dark matter or dark energy. And it doesn't tell us why the universe has the particular properties it does. Chapter 6. Black Holes, where physics breaks down.
Imagine an object so dense and massive that it warps space-time into a cosmic whirlpool from which nothing, not even light itself, can escape. This isn't science fiction. These objects are real, and they're called black holes. They represent some of the most extreme physics in the universe, where our normal understanding of space, time, and matter reaches its limits. The concept of a black hole was first imagined in the 18th century by Jean Michel and Pierre-Simon Laplace. They wondered, what would happen if you had a star so massive that the speed needed to escape its surface exceeded the speed of light? Since nothing can travel faster than light, nothing could escape such an object. It would be perfectly black, invisible against the cosmic backdrop. But these early thinkers were working with Newton's physics. It wasn't until Einstein's general relativity that we could truly understand black holes. Remember, in Einstein's universe, gravity isn't a force. It's the curvature of space-time itself. A black hole is a region where this curvature becomes so extreme that space-time essentially curves back on itself, creating a one-way trap. Black holes form from the death of massive stars, at least 3 times more massive than our Sun. Think of a star as being locked in an epic battle between 2 opposing forces. Gravity is constantly trying to crush the star inward, while the nuclear furnace at its core creates outward pressure that resists this collapse. For most of a star's life, these forces are in perfect balance.
But when a massive star exhausts its nuclear fuel, gravity wins decisively. The star's core collapses in less than a second, crushing matter to densities beyond imagination. If you could somehow compress the entire Earth to the density of a neutron star, it would fit inside a city. Compress it to black hole densities, and it would fit inside a marble, while still containing all of Earth's mass. At the center of a black hole lies what physicists call a singularity, a point where density becomes infinite and space-time curvature becomes infinite. This is where our physics breaks down completely. It's not just that we don't know what happens at a singularity. Our theories literally give nonsensical answers. It's like dividing by 0 in mathematics. You get infinity, which isn't really an answer at all. Surrounding the singularity is the event horizon, the black hole's point of no return. This isn't a physical surface you could touch. It's more like an invisible boundary in space. Cross this boundary, and you can never come back. The size of the event horizon depends on the black hole's mass. A black hole with the mass of our Sun would have an event horizon about 3 kilometers in radius. Here's something that sounds contradictory. Black holes don't actually suck things in like cosmic vacuum cleaners. If our Sun were suddenly replaced by a black hole of the same mass, Earth would continue orbiting normally. We'd just freeze to death without the Sun's heat. You'd have to get very close to a black hole to be trapped by it. But if you did venture close, you'd experience something called spaghettification. The gravitational pull on your feet would be significantly stronger than the pull on your head, stretching you vertically and compressing you horizontally until you resembled a piece of spaghetti. This tidal effect becomes more extreme as you approach the event horizon. Now, here's where things get really weird. Imagine you're watching a friend fall into a black hole. As they approach the event horizon, time dilation becomes extreme. From your perspective, your friend would appear to slow down, their image getting redder and dimmer as time stretches toward infinity. You'd never actually see them cross the event horizon. They'd appear frozen at the boundary forever. But from your friend's perspective, they'd cross the event horizon in a finite amount of proper time and continue falling toward the singularity. They might not even notice the moment they cross the boundary, especially for a massive black hole where the tidal forces at the event horizon are relatively gentle. This leads to one of the most profound puzzles in physics, the information paradox. Quantum mechanics tells us that information can never be truly destroyed. It can be scrambled or hidden, but never lost. However, anything that falls into a black hole appears to be gone forever, along with all the information it contained. This creates a fundamental conflict between quantum mechanics and general relativity.
Black holes also exhibit what's called the no-hair theorem. This mathematical result tells us that a black hole can be completely described by just three properties: its mass, electric charge, and spin, angular momentum. Everything else, what the black hole formed from, its composition, its history, is erased. It's as if black holes are nature's ultimate recycling machines, reducing all complexity to these three simple numbers.
Astronomers have discovered black holes throughout the universe. Stellar mass black holes, formed from collapsed stars, typically range from a few times the mass of our Sun to a few dozen solar masses. But at the centers of galaxies, including our own Milky Way, lurk supermassive black holes, containing millions or billions of solar masses. How these giants formed so early in the universe's history remains one of astronomy's great mysteries. We can't see black holes directly. By definition, they emit no light. But we can detect their effects on nearby matter. When material falls into a black hole, it forms an accretion disk, a swirling maelstrom of superheated gas that glows brilliantly as it spirals inward. Some of the universe's most energetic phenomena, like quasars and gamma-ray bursts, are powered by matter falling into supermassive black holes. The recent detection of gravitational waves, ripples in space-time itself, has opened a new window onto black holes. When two black holes spiral into each other and merge, they create gravitational waves that can be detected by incredibly sensitive instruments on Earth. These cosmic collisions convert more energy into gravitational waves than all the stars in the observable universe emit in light. Chapter 7. Black holes ain't so black. Hawking's greatest discovery.
Just when you thought black holes couldn't get any stranger, Stephen Hawking made a discovery that revolutionized our understanding of them. In one of the most elegant combinations of quantum mechanics and general relativity ever achieved, Hawking proved that black holes aren't completely black. They actually glow. This discovery emerged from Hawking's attempt to understand what happens when quantum mechanics meets the extreme curvature of spacetime near a black hole. Remember from our discussion of quantum mechanics that empty space isn't really empty. It's filled with pairs of virtual particles that pop into existence and almost immediately annihilate each other. These quantum fluctuations are happening everywhere, all the time, but they normally cancel out so quickly that we don't notice them. Near a black hole's event horizon, however, something remarkable can happen. When a virtual particle pair appears right at the boundary, one particle might fall into the black hole while its partner escapes into space. The escaping particle becomes real, carrying away energy, while the particle that fell in reduces the black hole's mass energy. From the outside, it appears as though the black hole is emitting radiation, what we now call Hawking radiation. Think of it this way. Imagine you have a savings account where you can temporarily borrow money, but you have to pay it back within a certain time limit. Normally, virtual particles do exactly this. They borrow energy from the vacuum and pay it back by annihilating each other. But near a black hole, one particle falls in, taking the debt with it, while the other escapes, keeping the borrowed energy. The black hole pays the debt by losing a tiny amount of its own mass.
This process means that black holes have a temperature and slowly evaporate over time. The temperature of a black hole is inversely related to its mass. More massive black holes are colder, while less massive ones are hotter. A black hole with the mass of our Sun would have a temperature of about 60 billionths of a degree above absolute zero. Incredibly cold. But a black hole with the mass of a mountain would be blazing hot, radiating energy at billions of degrees. Here's the paradox. As a black hole evaporates, it gets smaller and therefore hotter,
causing it to evaporate even faster. It's like a cosmic feedback loop. A black hole with the sun's mass would take longer than the age of the universe to evaporate significantly. But in its final moments, it would explode with the energy of millions of hydrogen bombs. Hawking radiation introduces one of the deepest puzzles in theoretical physics, the information paradox. When matter falls into a black hole, quantum mechanics says the information about its quantum state must be preserved somewhere. But Hawking radiation appears to be completely random, carrying no information about what fell into the black hole. If the black hole eventually evaporates completely, where does that information go? This paradox strikes at the heart of fundamental physics. Quantum mechanics absolutely requires that information be conserved. It can be scrambled or hidden, but never destroyed. Yet black holes seem to be perfect information destroyers. It's like having a paper shredder that's so thorough it erases the very concept of the documents you put into it. Hawking himself proposed various solutions to this paradox over the years. In 2004, he famously conceded a bet with fellow physicist John Preskill, acknowledging that information probably is conserved somehow, even in black holes. The most promising current idea is that information somehow gets encoded in the Hawking radiation in ways that are incredibly subtle, but preserve all the quantum information.
Recent theoretical work suggests that black holes might have firewalls, regions of extremely high energy that would incinerate anything crossing the event horizon. This idea challenges our notion that someone falling into a black hole would experience a smooth journey to the center. Instead, they might be vaporized the moment they cross the boundary. But this creates its own paradox, violating Einstein's principle that the laws of physics should appear the same to all observers. The information paradox has led to some of the most creative thinking in modern physics. Some theories suggest that the interior of a black hole might be connected to the exterior through quantum entanglement, a spooky connection that Einstein once dismissed, but that's now central to our understanding of quantum mechanics. Others propose that space-time itself emerges from quantum entanglement, making black holes natural laboratories for understanding the deepest nature of reality. Hawking's discovery that black holes radiate also means they have entropy, a measure of disorder or information content. Jacob Bekenstein had earlier suggested that a black hole's entropy is proportional to the area of its event horizon, not its volume. This was shocking, because normally entropy depends on volume. It's like discovering that the information storage capacity of a sphere depends only on its surface area, not how much space is inside it. This relationship between area and entropy has profound implications for our understanding of information in the universe. It suggests that all the information in any region of space can be encoded on its boundary, a principle now called the holographic principle. Your entire three-dimensional existence might be encoded on a two-dimensional surface, like a hologram. It's a mind-bending idea that reality as we perceive it might be a projection from a lower dimensional boundary. Chapter 8. The Origin and Fate of the Universe. Cosmic Biography. Every good detective story needs to answer two fundamental questions. How did it all begin? And how will it end? In the cosmic mystery that Hawking explores, these questions become, how did the universe begin? And what is its ultimate fate? The story of the universe's origin takes us back to the Big Bang. Not an explosion in space, but an explosion of space itself. Imagine trying to watch a movie of the universe's entire history. Run it forward, and you see galaxies flying apart, the universe expanding and cooling. Run it backward, and everything converges to a single point of infinite density and temperature, called a singularity,
But here's the fascinating part. Hawking and his colleague Roger Penrose proved, mathematically, that if general relativity is correct, the universe must have begun with such a singularity. It's not just that we think it probably did. The mathematics demands it. The laws of physics themselves break down at this point, just as they do at the center of a black hole. This creates a profound puzzle. How can we understand the origin of the universe if our physics breaks down at the very moment of creation? It's like trying to understand a story when the first chapter is written in a language that doesn't exist. The Big Bang Theory explains many observations beautifully. It predicts the abundance of light elements like hydrogen and helium, which matches what we observe. It explains the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. And it explains why the universe is expanding in exactly the way we observe.
But the standard Big Bang Theory also has some puzzling features that need explanation. Why is the universe so uniform? When we look at the cosmic microwave background, the temperature is almost exactly the same in all directions, even though widely separated regions couldn't have been in contact since the Big Bang. It's like finding that people in isolated villages around the world all decided to paint their houses exactly the same shade of blue without ever communicating. This puzzle led to the theory of cosmic inflation, proposed by Alan Guth. Inflation suggests that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, growing faster than the speed of light. This isn't a violation of relativity because it's space itself that's expanding, not objects moving through space. During inflation, a region smaller than a proton expanded to the size of a grapefruit in about 10 to the negative 32nd seconds. This incredibly rapid expansion explains why the universe appears so uniform. Regions that seem disconnected today were actually in close contact before inflation separated them. Inflation also explains another puzzle. Why is the geometry of space so close to perfectly flat? Just as inflating a balloon makes its surface appear flatter to an ant living on it, cosmic inflation stretched space so much that any initial curvature was flattened out. We live in what appears to be a flat universe, not because it started that way, but because inflation made it that way. But what about the universe's fate? This depends on a cosmic competition between the expansion of space and the gravitational pull of all the matter and energy it contains. If there's enough matter, gravity will eventually win, causing the expansion to slow, stop, and reverse in a big crunch, the time reverse of the Big Bang. The universe would collapse back into a singularity, perhaps to bounce back in a new Big Bang.
If there isn't enough matter, the universe will expand forever, gradually cooling and diluting until it reaches a state of maximum entropy called heat death. Stars will burn out, black holes will evaporate through Hawking radiation, and the universe will become a cold, empty expanse, filled only with elementary particles drifting farther and farther apart. Current observations suggest a third possibility. The expansion of the universe is actually accelerating, driven by mysterious dark energy that makes up about 68% of the universe's total energy density. This means we're headed for a big rip scenario, where the expansion becomes so rapid that it eventually tears apart galaxies, stars, atoms, and even space and time themselves. Hawking also explored a radical idea called the no-boundary proposal, developed with James Hartle. This suggests that asking what happened before the Big Bang is like asking what's north of the North Pole, a meaningless question. In imaginary time, a mathematical concept, not science fiction, the universe has no boundary or beginning. It's finite, but without edges, like the surface of a sphere. This proposal suggests that the universe is completely self-contained,
with no need for a creator to set initial conditions. The laws of physics themselves would determine not only how the universe evolves, but also how it begins. It's a beautifully elegant idea. The universe creates itself through the very laws that govern it.
Chapter 9. The Arrow of Time. Why yesterday differs from tomorrow. Here's a question that might seem obvious, but leads to profound mysteries. Why does time have a direction? Why do we remember the past, but not the future? Why do broken glasses never spontaneously reassemble themselves? Why does mixing milk into coffee create a uniform brown mixture, but we never see a cup of brown coffee spontaneously separate into pure black coffee and white milk? The answer lies in one of the most fundamental concepts in physics: entropy. Think of entropy as nature's way of keeping score of disorder. The second law of thermodynamics states that in any closed system, entropy always increases or stays the same. It never decreases on its own. This gives time its arrow. Hawking identifies 3 different arrows of time, and remarkably, they all point in the same direction. The thermodynamic arrow of time. This is the direction in which entropy increases. When you drop a glass and it shatters, the pieces scattered across the floor represent a more disordered state than the intact glass. The probability of those pieces spontaneously reassembling is so vanishingly small that it effectively never happens. This isn't impossible, just incredibly unlikely. To understand just how unlikely, imagine you have a box divided in half, with all the air molecules initially crowded into one side. If you remove the divider, the molecules will quickly spread throughout the entire box. The probability of them all spontaneously returning to one side is about the same as winning the lottery every day for the rest of your life. It's technically possible, but practically impossible. The psychological arrow of time. This is the direction in which we perceive time flowing and in which we remember events. Our brains are essentially entropy-measuring devices. We remember the past because our brains create ordered records of events that have already occurred, increasing the total entropy of the universe in the process. We can't remember the future because it would require our brains to spontaneously organize themselves in incredibly improbable ways. Think about memory formation. When you experience something, your brain physically changes. Neurons form new connections, proteins are synthesized, chemical traces are left behind. These changes increase the disorder in your brain and the surrounding environment, following the thermodynamic arrow of time. Remembering the future would require these changes to spontaneously reverse, which violates the second law of thermodynamics, the cosmological arrow of time. This is the direction in which the universe expands rather than contracts. We observe galaxies moving apart, not coming together. This arrow is deeply connected to the thermodynamic arrow through the initial conditions of the universe. The Big Bang represents the lowest entropy state in the universe's history. Everything was smooth, uniform, and highly ordered. As the universe expanded and cooled, gravity began to clump matter together, forming the complex structures we see today: galaxies, stars, planets, and eventually life itself. This process continuously increases the total entropy of the universe. But here's the remarkable thing. All 3 arrows point in the same direction, and this isn't a coincidence. Hawking argues that for intelligent life to exist and observe the universe, the thermodynamic and cosmological arrows must align. If we lived during a contracting phase of the universe, the thermodynamic arrow would reverse. Disorder would decrease, memories would work backward, and cause and effect would be reversed. Imagine living in such a universe. You'd see broken glasses spontaneously reassemble, coffee and milk unmix themselves, and heat flow from cold objects to hot ones. But you wouldn't actually see these things, because your brain would be running backward too.
unforming memories instead of creating them. Such a universe might exist, but no conscious beings could observe it. This connection between the arrow of time and the existence of conscious observers leads to a profound realization. Our very existence as thinking beings depends on the universe having started in a highly ordered state. If the Big Bang had begun with maximum entropy, complete disorder, there would be no arrow of time and no possibility of life or consciousness. The initial low entropy of the universe is one of the most remarkable facts about our cosmos. In a sense, we're living off the entropy debt created by the Big Bang. Every process that makes life possible, from the nuclear fusion in stars to the biochemical reactions in our cells, works by increasing entropy while creating local pockets of order. This raises a deep question. Why did the universe begin in such an ordered state? This isn't something the laws of physics require. In fact, a high entropy beginning would be far more probable. Some cosmologists suggest that inflation naturally produces a low entropy universe, while others invoke the anthropic principle. We observe a low entropy beginning because only such a universe could produce observers like us. The no-boundary proposal offers another perspective. If the universe has no beginning in imaginary time, then the question of initial conditions becomes moot. The arrow of time emerges naturally from the quantum mechanics of a universe without boundaries.
Chapter 10. Wormholes and Time Travel. Bending the Rules of Reality.
What if the universe had shortcuts? What if you could step through a doorway in New York and emerge in Tokyo, or even in the distant past? Welcome to the mind-bending world of wormholes and time travel, where Einstein's equations permit possibilities that challenge our deepest intuitions about space and time. A wormhole is exactly what it sounds like: a tunnel through space-time that connects distant regions or different times. Imagine space-time as a sheet of paper. Normally, to get from one point to another, you'd have to travel along the surface of the paper. But if you could fold the paper and punch a hole through both layers, you'd create a shortcut that bypasses the normal route through space. Einstein's general relativity doesn't just allow wormholes, it practically invites them. The equations describe how mass and energy curve space-time, and certain solutions to these equations naturally contain wormhole geometries. It's as if the universe's instruction manual includes blueprints for cosmic shortcuts. But there's a catch. There's always a catch in physics. While wormholes are mathematically possible, keeping them open and traversable would require something called exotic matter, matter with negative energy density. This is incredibly strange stuff that would fall upward instead of downward, and would make your bathroom scale read negative numbers. Think of it this way. Ordinary matter curves space-time inward, like placing a bowling ball on a stretched rubber sheet. To keep a wormhole open, you'd need matter that curves space-time outward, pushing the walls of the tunnel apart. This would require matter that violates what physicists call energy conditions, fundamental assumptions about how matter and energy behave.
We've never observed exotic matter in nature, and there are good reasons to think it might be impossible.
Quantum mechanics suggests that even empty space has a positive energy density due to virtual particle fluctuations. Creating regions of negative energy density might violate basic principles of quantum field theory. But let's assume for a moment that exotic matter exists and we could build a traversable wormhole. Could we use it for time travel? The answer is, surprisingly, yes, but with consequences that might make you think twice about trying it. Here's how it would work. Create a wormhole connecting 2 points in space. Take one end of the wormhole on a high-speed journey to a distant star and back. Due to time dilation, the slowing of time at high speeds, less time passes for the traveling end than for the stationary end. When the traveling end returns, you'd have a time machine. Step through one end, and you'd emerge from the other end in the past. But this creates the famous grandfather paradox. What if you traveled back in time and prevented your grandfather from meeting your grandmother? Then you would never be born, so you couldn't travel back in time in the first place. It's a logical contradiction that makes philosophers' heads spin. Hawking proposed a solution called the chronology protection conjecture. He suggested that the laws of physics conspire to prevent time travel to the past on a macroscopic scale. Whenever you try to create a time machine, quantum effects or other physical processes would destroy it before it could function. For example, as soon as a wormhole became a time machine, it would be flooded with virtual particles from the quantum vacuum. These particles would travel through the wormhole repeatedly, building up enormous energy densities that would destroy the wormhole in a burst of radiation. It's as if the universe has a built-in allergy to paradoxes.
The chronology protection conjecture isn't proven, but there's growing evidence that it might be correct. Every scheme physicists have devised for time travel runs into similar problems: quantum effects that prevent the time machine from working. It's as if nature has a no time travel clause written into its fundamental laws. But time travel to the future is not only possible, it's happening right now. Thanks to relativistic effects, astronauts on the International Space Station are traveling into the future at a rate slightly faster than those on Earth. Time dilation means that when they return to Earth, they've aged slightly less than they would have on the surface. For more dramatic time travel to the future, you'd need to travel at speeds close to the speed of light, or spend time near a massive object like a black hole. From your perspective, time would pass normally, but when you return to Earth, you'd find that much more time had passed there than for you. Hawking also explored other exotic possibilities suggested by general relativity. Cosmic strings, hypothetical one-dimensional defects in spacetime, could potentially create closed time-like curves if they existed and moved at high speeds. But like wormholes, cosmic strings would require exotic physics and might be prevented from causing paradoxes by quantum effects. The study of time travel isn't just science fiction. It's revealed deep connections between quantum mechanics, general relativity, and thermodynamics. Even if time travel to the past is impossible, understanding why it's impossible teaches us fundamental truths about the nature of spacetime and causality. Perhaps most importantly, the study of time travel highlights the remarkable consistency of physical laws. The same principles that govern the fall of an apple also regulate the most exotic possibilities in spacetime. The universe seems to be constructed in such a way that logical consistency is preserved, even in the most extreme scenarios we can imagine. Chapter 11. The Unification of Physics. The Quest for Everything. We've reached the final chapter of our cosmic detective story, and like all good mysteries, it ends with an attempt to tie together all the clues into one grand, unified solution. This is the quest for what physicists call a theory of everything, a single framework that would explain every force, every particle, and every phenomenon in the universe. Think of physics today as being like a beautiful but incomplete symphony. We have wonderful movements: general relativity describing gravity and the large-scale universe, quantum mechanics describing the atomic world, the standard model cataloging particles and forces. Each movement is magnificent on its own, but they don't quite harmonize when played together. The goal of unification is to find the underlying musical theme that makes sense of the entire composition. The problem is that our two greatest theories, general relativity and quantum mechanics, are fundamentally incompatible. General relativity is smooth and deterministic, describing a universe where spacetime curves gently under the influence of matter and energy. Quantum mechanics is choppy and probabilistic, describing a universe where particles pop in and out of existence and reality itself seems uncertain. Most of the time, this incompatibility doesn't matter. General relativity governs planets and galaxies, while quantum mechanics governs atoms and molecules. They operate in different realms, like two people speaking different languages who happen to live in different countries. But in extreme conditions, inside black holes, during the first moments of the Big Bang, at the Planck scale where quantum effects become important for gravity, both theories are needed simultaneously, and they give contradictory answers. The first step toward unification was the electroweak theory, developed in the 1960s. This showed that at high energies, the electromagnetic force and the weak nuclear force merge into a single electroweak force.
It's like discovering that two apparently different rivers actually spring from the same source high in the mountains.
This success inspired physicists to attempt grand unified theories that would unify the electroweak force with the strong nuclear force. These theories make striking predictions. They suggest that protons, once thought to be perfectly stable, should occasionally decay. They also predict that the universe should contain equal amounts of matter and antimatter, which conflicts with observation since we clearly live in a matter-dominated universe. Grand unified theories also predict the existence of magnetic monopoles, particles that would be like magnets with only a north pole or only a south pole. Despite extensive searches, none have been found. This doesn't necessarily disprove grand unified theories, but it suggests that if they're correct, the energy scales involved are far beyond anything we can currently test. The ultimate goal is to include gravity in this unified framework, creating a true theory of everything. This requires a theory of quantum gravity, a description of gravity that incorporates the principles of quantum mechanics. This is extraordinarily difficult because gravity is so much weaker than the other forces. To probe quantum gravitational effects directly would require particle accelerators the size of galaxies. The leading candidate for a theory of everything is string theory. This radical approach suggests that the fundamental constituents of reality aren't point particles, but tiny, vibrating strings. These strings are unimaginably small. If an atom were enlarged to the size of the solar system, a string would still be smaller than a tree. Different vibrations of these strings correspond to different particles, like different notes played on a violin string. An electron is one vibration pattern. A photon is another. A quark is yet another. In this view, the rich complexity of particle physics emerges from the simple concept of vibrating strings. String theory requires extra dimensions beyond the three of space and one of time that we experience. The theory works mathematically only if space has 9 or 10 dimensions. The extra dimensions are compactified, curled up so small that we don't notice them in everyday life. It's like viewing a garden hose from a great distance. It appears one-dimensional, but up close you can see it has thickness and circumference. The way these extra dimensions are curled up determines the properties of particles and forces that we observe. Different configurations of these hidden dimensions could produce universes with completely different physics. This leads to the unsettling possibility of a multiverse, an enormous number of possible universes, each with different laws of physics. String theory has evolved into M theory, which includes not just strings but also higher dimensional objects called branes, short for membranes. Our entire three-dimensional universe might be a brane floating in a higher dimensional space. This could explain why gravity is so weak compared to other forces. It might be leaking into the extra dimensions. Despite its mathematical elegance, string theory faces serious challenges. It makes few testable predictions at energies we can achieve, leading critics to argue that it's not science, but mathematics. The theory has an enormous number of possible solutions, perhaps 10 to the power of 500 different ways to configure the extra dimensions, making it difficult to extract unique predictions. Alternative approaches to quantum gravity include loop quantum gravity, which suggests that space and time themselves are quantized, made of discrete, indivisible units at the smallest scales. Another approach, called emergent gravity, proposes that gravity isn't fundamental, but emerges from more basic quantum phenomena, like temperature emerges from the motion of molecules. The quest for unification has already yielded profound insights. It's revealed deep connections between seemingly unrelated phenomena, and has led to a better understanding of black holes, the early universe, and the fundamental nature of space and time. Even if we never achieve a complete theory of everything, the journey toward it continues to illuminate the deepest mysteries of existence. Hawking believed that if humanity ever discovered a complete, unified theory, it would be the ultimate triumph of human reason. We would finally understand the mind of God, so to speak, not in a religious sense,
but in the sense of comprehending the fundamental laws that govern all of reality. It would answer not just how the universe works, but why it works the way it does. But even a theory of everything wouldn't answer every question. We'd still need to understand why the universe exists at all, why consciousness emerges from matter, and what our purpose might be in this vast cosmos. Science can tell us how the universe works, but questions of meaning and purpose lie beyond its scope. Conclusion: the wonder of it all. As we reach the end of our journey through Hawking's cosmic detective story, let's step back and marvel at what we've discovered. We began with ancient humans looking up at the night sky and creating stories about turtles supporting the Earth. We end with modern physicists contemplating multidimensional strings vibrating in hyperspace and black holes that radiate themselves out of existence. The distance between these two worldviews is staggering, yet they're connected by an unbroken chain of human curiosity and reasoning. Each generation of scientists stood on the shoulders of those who came before, seeing a little further, understanding a little more. Galileo built on Copernicus, Newton built on Galileo, Einstein built on Newton, and Hawking built on Einstein. What makes Hawking's contribution so remarkable is not just his discoveries, though Hawking radiation alone would secure his place in history, but his to share the wonder of these discoveries with the rest of humanity. He showed us that the universe is stranger and more wonderful than we ever imagined, yet still comprehensible to human reason. Through his work, we've learned that time and space are not the fixed stage on which cosmic events play out, but dynamic participants in the drama. We've discovered that the universe is expanding, carrying galaxies apart like raisins in rising bread. We've found that black holes, the universe's ultimate prisons, actually glow with radiation and will eventually evaporate into nothing. We've seen that the arrow of time is connected to the growth of entropy, and that our very existence depends on the universe having started in an incredibly ordered state. We've explored the possibility of wormholes and time travel, only to find that the universe seems to protect itself from paradoxes. And we've glimpsed the possibility of a theory of everything that might finally reveal the deepest laws of reality. But perhaps most importantly, Hawking reminded us that science is not just about collecting facts. It's about seeing the connections between things, about understanding the deep patterns that underlie surface appearances. When you realize that the same quantum uncertainty that prevents atoms from collapsing also creates the virtual particle pairs that make black holes evaporate, you're seeing the profound unity that underlies the apparent diversity of phenomena. The universe Hawking revealed to us is not the clockwork mechanism that Newton imagined, or the static cosmos that Einstein initially preferred. It's a dynamic, evolving, quantum mechanical universe where uncertainty is fundamental, where space-time itself can ripple and stretch, and where the very vacuum of space seethes with virtual particles popping in and out of existence. This universe is stranger than fiction, yet it follows mathematical laws that human minds can comprehend. This is perhaps the deepest mystery of all. Why should the universe be mathematically beautiful? Why should equations scribbled on blackboards by physicists correspond so precisely to the behavior of distant galaxies and subatomic particles? Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." We are collections of atoms that have somehow organized themselves into beings capable of contemplating the cosmos. We are the universe becoming aware of itself, matter achieving consciousness, and looking back at its own origins. Hawking's greatest gift was showing us that this scientific worldview doesn't diminish the wonder and beauty of existence. It enhances it. When you understand that you're made of atoms forged in the cores of ancient stars, when you realize that your brain is a quantum mechanical system capable of pondering the deepest laws of physics, when you grasp that you're participating in a cosmic story that began 13.8 billion years ago and will continue for trillions of years into the future, how can you feel anything but awe?
The quest for understanding continues. There are still mysteries to solve, still questions to answer. We don't yet have a theory of everything. We don't understand dark matter or dark energy. We don't know if string theory is correct, or if there are other universes beyond our own. The cosmic detective story that began with ancient astronomers continues with each new generation of scientists. And that's exactly as it should be. The joy is not just in the destination, but in the journey itself, in the process of discovery, in the moment when a new piece of the cosmic puzzle clicks into place, in the gradual unfolding of nature's deepest secrets. We are all participants in this grand adventure of understanding, each of us carrying forward the flame of curiosity that has illuminated humanity's path from the caves to the cosmos. As Hawking himself said, "We are just an advanced breed of monkeys on a minor planet of a very average star." But we can understand the universe. That makes us something very special. In a universe vast beyond imagination, in which we are smaller than specks of dust, we can still comprehend the laws that govern everything from quarks to quasars. That is our gift, our responsibility, and our greatest adventure. The universe is not only queerer than we suppose, it is queerer than we can suppose. But it is not beyond our ability to understand. And that understanding is perhaps the most beautiful thing of all. Welcome to the Cosmic Detective Story. The mystery continues, and you are now part of it. This concludes tonight's tale. Until next time, good afternoon, good evening, and good night.